Hello and welcome back to eTech Video Production. This video is segment 3 of 6 on Cisco Enhanced Interior Gateway Routing Protocol or EIGRP. Segment 3 is the deep dive of EIGRP. In this video segment we have 3 objectives. The first objective is path manipulation. By manually alter the bandwidth, delay, and the use of offset list, we can easily influence EIGRP path selection to a remote network. The next objective is variance command. In routing, the term load balancing is the router's capability to load sharing over 2 or more interfaces to the same remote destination network. However, to enable the load balance, all those interfaces must have the same metric to the remote network. EIGRP is the only routing protocol that can actually load balance over unequal metric paths. Using the variance command, we'll enable that and see how that actually works. And our last objective is filter incoming or outgoing route advertisement. We'll demonstrate how to filter incoming or outgoing route advertised with the use of distributed list and route filter. Prior diving into these lab objectives, let's quickly review the lab topology. Here is the network topology that we'll be using throughout this video segment. In this topology, I have the core switch with IP routing enabled and running as a layer 3 switch. Upstream of the core switch is router 0, where it's connecting with router 1 and router 2, and they are connecting with router 3 in a loop or a partial mesh. The core switch, router 0, router 1, router 2, router 3, and the gigabit 00 interface of the firewall is currently configured for EIGRP under the autonomous system number 10. Behind the core switch is 4 VLANs on 172.16 networks. As the core switches perform EIGRP summarization for those 172.16 in a 172.16.0.0/22 to router 0. On interface gigabit 03 of router 0, router 1, router 2, and router 3 is a PC to simulate its LAN on 192.168, followed by the router number respectively. Router 0 is also performing EIGRP summarization for 192.168.0.0/22 back to the core switch. And last, between router 3 and the firewall, we are performing EIGRP authentication for autonomous system number 10. If you are interested in this current EIGRP configuration, please review our video segment 2 on Cisco EIGRP. So without further ado, let's perform those objectives of this video segment. Our first objective is path manipulation. Currently, all networks behind router 0 to reach the 192.168.3.0 and the Internet, router 0 will load balance via router 1 and router 2 as both paths have the same metrics. However, the company wants us to manipulate router 0, so router 0 will only take the router 1 path when it's available and only use router 2 when that path is not available. So let's consult to router 0 and take a look at its current EIGRP routing table. Here's the routing table for router 0 for the default route and 192.168.3.0 here. It is load balancing between router 1 and router 2. As you can see, both of them have the same metrics. Let's take a look at the topology table. And you can see it's pretty much the same as the routing table. For 192.168.3.0, I have 2 successor. Both metrics are the same. And down here, the default route, 2 successor, and both metrics are the same. Let's take a look at the current bandwidth on gigabit 02 on router 0. Show interface gigabit 0/2. Currently, the bandwidth is set for 1 million kilobit or 1 gigabit. Let's change the bandwidth down to 900,000 or 900 megabit per second. And you can see they are in kilobits, so that is 900,000 kilobit per second. Let's take a look at the topology table now. Now for 192.168.3.0, only one successor, where the feasible distance is 3,328, where the feasible successor is 3,584. The same for the default route, one successor. The feasible distance is 3,584, where the feasible have a metric of 3,840. Let's take a look at this routing table. The default route only have one path via 10.0.0.6, which is route 1, same as 192.168.3.0 via router 1. Here's a precaution when changing the bandwidth on a router to manipulate upstream network. What we did is manipulate gigabit 02, and it affects how router 0 go upstream. However, from router 3 perspective, going back, that change does not affect router 3. Let's console to router 3 and take a look at this routing table. Here I'm on router 3. Show IP route. Here you can see for both 172.16/22 network and 192.168.0.0 is still load balancing between router 1 and router 2. So by manipulate the bandwidth on gigabit 02, telling router 0 to take router 1 path to reach those network, but the returning data from router 3, especially when you use UDP, it might send it to router 2 back into router 0, which possibly can cause a problem. So if you're going to change the bandwidth on an interface, you should also change the bandwidth of the upstream router to match. Let's console to router 2 and do that. Here on router 2, interface gigabit 0/0 and bandwidth 900,000 kilobit or 900 megabit per second. Now let's go back to router 3. Now it's no longer load balanced for the entire 172.16/22 and 192.168.0.0, as its path is via 10.0.13, which is router 1 interface. As you can see, changing the bandwidth of an interface, we can easily force EIGRP to choose the path that we want. If you recall the EIGRP composite matrix, where it included the bandwidth, load, delay, reliability, and MTU. However, K1, which is the bandwidth, and K3, which is the delay, by default is 1. So let's perform this path manipulation lab again, but this time we will change the delay of an interface. Let me reset all routers back into its original configuration before we jump on the delay. And we're back in router 0. Let's take a look at its routing table. And you can see it's load balanced for the default route as well as 192.168.3.0. Let's review the gigabit 02 interface pointing to router 2. Earlier we manipulate the bandwidth by lower the bandwidth and increase the metrics. This time let's change the delay. By increase the delay, it will also increase the metrics for this path. And the delay in tenth of microsecond, I want to change it to 20 microseconds, so the value is 2. Let's take a look at the interface again. Now the delay is 20 microseconds. Let's take a look at the routing table. And we no longer load balance for the default route as the path is router 1. Same thing for router 3 via 10006. And don't forget to change the delay on gigabit 00 on router 2 for path coming back. Let's do a quick recap of what we did so far. We start with manipulate the bandwidth, then the delay on interface gigabit 02 on router 0, which increase all metrics to remote network via router 2, and force EIGRP to detect router 1 path to reach the 3.0 and the internet. Well, this is a good exercise in a lab environment, but in a real-world environment, we're wasting this 1 gigabit bandwidth between router 0 and router 2. So in the real-world environment, this is what you want to do. To reach the 3.0 network, router 0 will take router 1 path, and for the internet, it will take router 2 path. Now that's what I call network optimization, and with the use of offset list, we can achieve that. So let's reset router 0 back to initial configuration and heads on to the offset list lab. And we're back in router 0. Let's see what this routing table look like. And we can see it's load balance for the default route and 192.168.3.0 via router 2 and router 1. Let's see what the topology table look like. And here you can see for the 3.0, 2 successor via router 1 and router 2 were both feasible distance, and the advertised distance is exactly the same. Let me go over the offset list and see what it's actually doing. Since we want router 0 to take router 1 path to reach the 3.0 network, but both router 1 and router 2 is currently advertised distance is 3072 on both of these interfaces. So this is how offset lists work. We start first by creating an access list that capture the 3.0 subnet. After that, we go underneath router EIGRP, and with the command offset list followed by the ACL name or number, then in the indirection, since router 2 is advertising to us, we're going to add a value of 20 into that on gigabit 0/2. What that does is that 3072 here, it will add 20 to that, become 3092. Now router 0 will take router 1 as a successor and router 2 as a feasible successor. Let's apply this offset list the same way we did here and see how that works. We start first by create the ACL. We'll call it R3 subnet and permit 192.168.3.0. Next we'll go in router EIGRP 10. Then the command offset list, followed by the ACL name, which is R3 subnet. In the indirection, and we're going to add a value of 20 on gigabit 0/2. We'll wait for EIGRP to converge. And it had converged. So let's see what the topology table look like. Here you can see only one successor, and the feasible distance is 3028, which is router 1 there, where router 2, the advertised distance now is 3092, and the total cost is 3348. So let's do the same thing for the default route. We'll create an ACL that captures the default route. Then under EIGRP on gigabit 01, we're going to add a value into that path for EIGRP to take router 2 for the default route. So let's start by creating an ACL that captures the default route. We'll call it default route. Here actually the first thing we need to do is deny the 192.168.3.0. Then permit any. As we only want to add 20 yes for the default route, not 192.168.3.0. Now underneath router EIGRP 10 offset list, and the name of offset list is default route. In the indirection, and we add 20 on gigabit 0/1. The interface pointing to router 1. Again, we'll wait for conversion. Show IP EIGRP topology. Now only one successor. The feasible distance is 3584, which is router 2.10 there. The advertised distance via router 1 is now 3348, where router 2 only 3328. And last, the routing table. And we're no longer load balancing for the default route, as the best path is via router 2, and for 192.168.3.0 is via router 1. Let's console to the business computer and perform a trace route to 192.168.3.10, which is PC3, and Google to see which path does it take. Here we're on the business computer, so trace to 192.168.3.10. First hop is the default gateway, which is the core switch, then 10.00.2, which is gigabit 00 on router 0, then 10.0.0.6, which is router 1. So it's going via .6, which is router 1. Let's trace to Google. And it's going via router 2.10. While we're here, let's do a failover test. I'm going to send a constant ping to 192.168.3.10. That's the wrong command, so ping 192.168.3.10 and send 1000 ping. 1000 ping there. So what we're going to do is expand the link between router 0 and router 1. As you can see the interface go down there. And just go on the other path. Stop there. And let's do a trace route to 3.10. And now it's going via router 2. And that, my friend, is how offset lists work. I do want to show you one more thing about offset list. Let's resume this link between router 0 and router 1. Currently we apply the offset list in the in direction, influence how router 0 choose a path to reach the remote networks. But on router 3 it's still load balancing going back. Let's take a look at router 3 routing table. And you can see for the 172 and for 192.168.0.0 is load balancing. So if we want router 3 to take router 2 path to reach all the VLANs behind the core, we can create an offset list and apply it on gigabit 01 and increase the metrics this way. But I'd like to show you a different way. I can create an ACL that capture all these VLANs right here on router 0 and increase the metrics on gigabit 01 in the out direction, or when I advertise to router 1 I will add 20 to that. So let's do that. So let's console to router 0, create the ACL that capture those 172 subnet, called standard, and we'll call it VLAN ACL, and permit 172.16.0.0 followed by 0.0.3.255. One too many zero there. Now under EIGRP 10, offset list, the name of my ACL. This time in the out direction I will add 20 on gigabit 0/1. We'll wait for the conversion. Now let's go back to router 3. Remember, for 172 we are load balancing. So let's say show IP router EIGRP. And now 172.16.0.0/22 is only one path via .17. And .17 is router 2. So you can see the offset list is not only for incoming advertisement, it's also for outcoming as well. Next on the list of exercise in this video segment is unequal cost load balancing. I've cleared all the commands from the previous lab, so let's take a look at the routing table for router 0. Show IP route EIGRP, and you can see it's load balancing for the default network as well as 192.168.3.0 network. For this unequal cost load balancing, I want to change some initial configuration. Currently both links between router 0 and router 1 is set at 1 gigabit per second. I want to make a change to the link between router 0 to router 2 at half of that, which is 500 megabit per second. And bandwidth 500,000 kilobit per second. Show interface gigabit 0/2. and it is set at 500 megabit per second. Now let's take a look at the routing table again. And we are no longer load balanced for the default route as well as 192.168.3.0 networks. Our only path is via router 1, 10.0.0.6. Let's also take a look at the detail for the default route. So IP route for 0.0.0.0. Here, the next hop is 10.0.0.6. I learned that from 10.0.0.6 via gigabit 01. The metric is 3,584. Traffic share count is 1 since that is the only route. Let's take a look at the topology table. And you can see here for the default route only one successor. Feasible distance is 3,584, which is router 1. And we have a feasible successor or backup route via router 2, and the metric is 6,144. Let's scroll up to take a look at the 3.0 network. Only one successor. Metric is 3,328, where the feasible successor is via router 2 at 5,888. One of my favorite things about EIGRP is that unlike OSPF or RIP or ISIS, EIGRP also supports unequal cost load balancing with the use of variance command. I want to pause right here and explain to you how the variance command actually works. I'm going to focus on router 0, how to reach 192.168.3.0. Currently, the links between router 0 and router 1 is at 1 gigabit per second, where EIGRP metric is 3,328, and the links between router 1 and router 2 is set at 500 megabit per second, with a metric of 5,888. And one more time, all other routing protocols, including EIGRP by default, the best metric is the only path to reach the remote networks. However, with the use of variance command, we can change that for EIGRP. Under EIGRP, you can use the commands variance followed by a multiplier, which is a number. For example, I'm going to use a multiplier of 2. What that does is take the feasible distance of 3,328 and multiply by 2, which equal to 6,656. Any feasible successor when the total metric is less than this number, EIGRP will bring that route into its routing table and load sharing. There is 2 conditions for unequal cost load balancing. Number 1, you must be a feasible successor. Number 2, the metric for the feasible successor must be less than the feasible distance, which is the metric for the successor multiplied by the variance multiplier. Let's console back to router 0 and implement the command variance 2. I'm back in router 0, so let's implement the command variance. And you can see the variance multiplier. Let's use 2. Let's take a look at the routing table. Here you can see we are now load balanced for the default route as well as 192.168.3.0, and the metrics are different. 6,144 via router 2, where 3,584 via router 1, here 5,088 via router 2, and 3,328 via router 1. Let's take a look at the topology table. And you can see 2 successor but the metrics are different. And if you're wondering about how EIGRP load balance, like people going this way is faster than the people going this way, actually the guy who came up with the variance command probably wasn't drinking at the time and thought about it already. Let's see how EIGRP load balance for the 192.168.3.0 network. Show IP route 192.168.3.0. The traffic share count for the slower link is only 17, where the faster link is at 30, as the metrics for the slower link is slightly less than half of the twice of the feasible distance. I want to cover one more thing before we close out this variance command lab. Remember, one of the conditions to enable the unequal cost load balancing, the total metric for the feasible successor here is 5,888, must be less than the feasible distance multiplied by the multiplier. Let's show the IP protocol. Here, EIGRP of autonomous system number 10, the variance is 2. What happens if this bandwidth is only at 250 megabit per second? Let's change the interface bandwidth on gigabit 02 to 250 megabit per second. Now let's take a look at the routing table. We are no longer load balanced for the default route or 192.168.3.0. Let's show the topology table. The feasible successor is still there. The cost is 11,000 for 192.168.3.0, as well as the default route. The feasible successor cost is 11,000 as well. So if we change the variance to 4, that will be around 14,000. Then the feasible successor will be copied to the routing table for unequal cost load balancing. Let's go back to EIGRP. Variance 4. Now show IP EIGRP. Show IP route EIGRP. Now we're back into unequal cost load balancing for the default route as well as 192.168.3.0. And last, let's take a look at the load sharing. Now the load sharing is 73 to 240. Now you can see why EIGRP is one of the unique routing protocol. With the using of variance command, you can perform unequal cost load balancing. But before you run back and start changing your dynamic routing protocol for your interior gateway routing protocol to EIGRP, thinking about why your organization was using OSPF in the first place. Let's reset our routers and continue with the next lab. Next objective in this video is route filtering using distribute list. Using the distribute list command, we can filter which route to advertise or receive and apply it globally, which is all neighbors, or to a specific neighbor. There are two steps to this. First, create an ACL to permit or deny that specific route you want to filter. Second, under EIGRP configuration, use the command distribute list followed by the ACL created in step 1, then in or out direction. This will apply this filter to all neighbors or globally, or you can continue to specify an interface to target a specific neighbor. To demo this objective, I will perform two exercises. For the first exercise, we will write an ACL to the 9.192.168.0.0 while permit everything else on router 0. Then apply that ACL using the distribute list globally in the out direction, which is to all neighbors, so no routers in our autonomous system will know about this network. For the second exercise, using the same method, we will filter only the business and engineering department and advertise that only to router 1, while the sales and financial VLAN subnet only to router 2. I'm going to hit pause here and make myself a cup of coffee, then we'll continue with the lab. And I'm back. Our first exercise here is to filter out 192.168.0.0 so no other routers in autonomous system 10 will know about it. We'll start by taking a look at the routing table for the core switch and router 3 to see if they know about that network. Here at the core switch, let's review its routing table. And you can see it does know about 192.168.0.0. Let's go to router 3. And it is load balancing for 192.168.0.0 via router 2 and router 1. So we'll go back to router 0. We'll start by create the access list, IP access list, and it can be standard. We'll call it router 0 subnet, and we'll deny 192.168.0.0. Here we need to permit anything else. If we don't, router 0 will filter all advertised routes from its neighbor and do not forward to any other neighbors. Now we need to apply, so we'll go underneath EIGRP, and the command is distributed list followed by the access list number or the name of our access list. In the in or out direction, this will be out, and I'll end it here as it applied this access list globally. We'll wait for the conversion with all 3 neighbors, and the conversion has happened. Let's go back to the core switch. And 192.168.0.0 is no longer in this routing table. Let's take a look at router 3. And on router 3 as well. While we're here in router 3, let's take a look at all the 172.16 subnet. Currently it's load balanced between router 2 and router 1. So our next exercise, we want to know the business and engineering will go to router 1, while the sales and finance will go to router 2. So we need to go back to router 0 and create 2 ACL. Let's create a name access list to capture the business and engineering department VLAN subnets. IP access list. We'll do standard again and call it biz ENG_subnet. Permit 172.16.0.0 with an inverse mask of 1.255. That would cover 172.16.0.0 and 1.0. Now another access list to capture the sales and financial department. Standard sales finance _subnet. Now 172.16.2.0 Well, card mask of 001255 should cover 2.0 and 3.0. Now we go underneath EIGRP by router EIGRP 10. We start with the distribute list, the business and engineering subnet in the out direction on gigabit 01. We'll wait for the conversion with router 1. And we have conversion with router 1. Let's apply the next one. Sales and finance subnet in the out direction on gigabit 0/2. While we're waiting for the conversion, again, you can apply this distribute list ACL in the in or out direction. And we have conversion. Let's go back to router 3. IP route EIGRP. And we no longer load balance as the 172.16.00 and 10. The next hop is .13, which is router 1. And for 172.16.2.0 and 3.0, the next hop is .17, which is router 2. Now you can see route filtering for EIGRP using distribute list is quite simple. Let's do this all over again, but this time we'll use Prefix-List. And the last objective in this video segment is route filtering using distributed list, but this time we will use Prefix-List instead of ACL. Prefix-List works just like an access control list, but typically used in route maps and route filtering operation. It is far more flexible than a simple access control list due to you can specify a range of prefixes with the operation of GE, which is greater than or equal to, and or LE, which is less than or equal to a certain prefixes. Here are a few examples of Prefix-List. The first example must match 0.0.0.0/0, which is the default route only. The second example is 0.0.0.0/0 all the way to less than equal to /32, which match all networks. The third example, only 192.168.1.0/24. The fourth example, 192.168.1.0/24, 25, 26, 27, and less than or equal to /28. And the last example, 192.168.1.0/24, but must be from 26 to less than /30, which is a mask of 192 all the way to the 252. I will try to post a video with more detail on Prefix-List, so please click that subscribe button below and join our video channel as you can search for the Prefix-List video. And back to the configuration lab. We'll perform the route filtering the same way as previous lab, but this time using Prefix-List. The first exercise is to filter out 192.168.0.0 on router 0 while allowing all other advertised networks. I have reset router 0 back to its original configuration, so here at the core switch you can see it does know 192.168.0.0 as well as router 3. It load balance for 192.168.0.0. Here in router 0, we'll create our prefix list with the command IP prefix list. We'll give it a name, router 0 subnet, followed by a sequence number. I'll give it number 10. Then we need to deny 192.168.0.0/24. Next is sequence 20. This time we'll permit all routes. Now we will apply this prefix list using the distribute list under EIGRP. The prefix and the prefix list name router 0 subnet in the out direction, which is all neighbors. We'll wait for the reconversion with all neighbors. There we go. Now we go back to the core switch. And network 192.168.0.0 has disappeared on router 3. And network 192.168.0.0 no longer there. Next we're going to create two more prefix lists. The first prefix list will match the business, department, and engineering subnets. And on router 0 we'll filter that prefix list to router 1. The second prefix list will capture the sales and the financial department, as we'll filter that toward router 2. Let's review the routing table for router 3. It knows all four 172.16 networks and load balance between router 1 and router 2. We're back in router 0, so let's create the two prefix lists. One to capture the business and engineering VLAN subnet, and the other one to capture the sales and financial VLAN subnet. We'll call the biz eng_subnet. This time I don't need the sequence command, as this is the only network I want to capture. So permit 172.16.0.0/23, but less than equal to 24. That will capture 172.16.0.0 and 10. Let's create the second one. We'll call it the sales subnets. Permit 172.16.2.0/23, but less than equal to 24. Now let's go underneath the EIGRP and apply these. The business and engineering subnet in the out direction on gigabit 01. We'll wait for the reconversion with router 1. And we have conversion with router 1. Let's apply the second one. Sales and financial subnet in the out direction on gigabit 02. And we have full conversion. Let's go to router 3. As you can see here, no more load balancing, as 172.16.0.0.10. Next hop is .13, which is router 1. And for the 2.0 and the 3.0, the next hop is .17, which is router 2. So the prefix list works just like the ACL for distributed lists or route filtering, but it allows us to be more flexible on certain prefix range than access control list. Let's do a quick recap of this video segment, the deep dive of EIGRP. First, we went through path manipulation. By altering the bandwidth and the delay of an interface, we force EIGRP to take one path through a remote network. We follow up with the use of offset list and allow us to have more granular controls and force EIGRP to choose the path we want it to take. We follow up with the Variance command, which allow EIGRP to load balance over multiple paths even though they have different metrics. And last, we went over route filtering with the Distributed List command with both ACL and Prefix-List. I'd like to thank you for watching part 3 of our EIGRP video segment, The Deep Dive. I hope this somewhat clarifies some of your questions you have on EIGRP, as well as giving you some idea how to optimize your network. So if you like this video, give us a thumb up, as well as subscribe to our video channel. Meanwhile, stay safe as I'll see you in part 4 video.